What are you doing?
Laughing.
Kannst du Schlüssel bei der Sekretärin oben abholen? Good afternoon, everybody. So we are going to have summary and question and hopefully answer session today. Before we start with that, I wanted to make you aware of one point on the lecture website. But now I lack network connection. So if I press on the respective button, it will not load. I have to show this here. I put a collection of problem sheets, which of course you already know here, but now they contain solutions. I did not include the exam yet. Sorry for that. Huh? Okay. Maybe the network connection returns. So, yeah, makes me nervous. No? Yes, no. Why is it wrong? It's ITP AP. Okay. So what was this lecture about? I wanted to familiarize you with a new analytic theory of nonlinear cosmic structure formation. That's the point. Now, why new? Because old is not good. I told you why. Previous attempts to analytically describe cosmic structure formation begin either with the hydrodynamical equations or they use the density contrast, matter density contrast, as the primary field. The hydrodynamical equations fail because the assumptions underlying these equations are not satisfied. In particular, the hydrodynamical equations, Euler equations, assume that there is a smooth and uniquely valued velocity field, and this is not the case. Similarly, if you work with the density field as the variable that you try to understand, then it's easily possible by only slightly converging matter flows to create very high density contrasts, and this leads to problems very early on in the process of approaching nonlinear structures. So we designed a different approach, and this different approach is this kinetic field theory of cosmic structure formation that we talked about. What's the point? The point is that in this theory, we use a completely different variable to describe the evolution of cosmic structures, namely the trajectories of particles in phase space. Now, why is this important? First of all, we can describe the unperturbed trajectories by a Green's function. And that is, we can incorporate the knowledge of how trajectories evolve by integrating the Green's function into the generated function of the theory. Second point is particle trajectories in phase space cannot cross, because each phase space point is a unique description of state of a microscopic particle in classical mechanics, and it fixes the complete initial conditions for integrating the Hamiltonian equations. This means that if two trajectories would cross in phase space, from that point on, they would have to follow the same trajectory. The next reason for developing kinetic field theory was that, as I said, even small perturbations of trajectories relative to a fiducial evolution, a fiducial trajectory, can lead to very high density fluctuations. So this means that comparing actual particle trajectories to fiducial or free particle trajectories is a much better suited quantity, much better suited variable than, for example, the density contrast is. All right, so these were the reasons. Now, we call this kinetic field theory because it's kinetic and it's a field theory. Okay. It's appropriate, isn't it? Now, what's the field? The field is the complete bundle of particle trajectories. And the unknown, the uncommon aspect of that is that our field is distribution valued. Right? You have a field value at each point in space, and this value is either 0 or it's the peak of a delta function. So it's a distribution valued field. And this is why our dynamical equations do not directly operate on the field, but we describe all the trajectories by the Green's function. Now, the theory is kinetic because it integrates over details of a microscopic theory and describes an entire ensemble of particles rather than the individual evolution of individual particles, of microscopic particles. All right, now we could have spoken about this theory in exactly the same way as we did in view of its application to cosmology, with many different with having many different possible applications in mind. Because if you remember what we did in order to set up the theory was, first of all, we needed probabilistic description of an initial state of a particle ensemble without reference to cosmology. All we assumed was that, first of all, we have a Gaussian random field. And second, from this Gaussian random field, we draw particle positions and particle momenta. There was no reference to cosmology in doing that. Right? We just drew these quantities from that initial assumed Gaussian random field. I told you why assuming Gaussianity is a good idea, because of the central limit theorem. Because in every process that superposes density fluctuations, for example, in a way such that the individual fluctuations in the density field are independent of each other and are drawn from the same parent distribution, will inevitably create a Gaussian random field. So Gaussianity is not a severe restriction, and this is why we refer to Gaussianity in the first place. Now, of course, we can apply this to cosmology, but now in this summary, I wanted to deliberately keep the structure of the theory and the cosmological application more separate than we did in the lecture. All right, so you need a probabilistic description of the initial state, and we use the Gaussian random field underlying. There we assume that density fluctuations and momentum fluctuations are correlated. And the reason why we did was that they are both controlled by the continuity equation. which says that whenever you have a positive density fluctuation, you will also have, or you are also likely to have, a converging matter flow. This is important. This doesn't need to be the case. Right? Depending on the application for KFT that you may have in mind, density fluctuations and momentum fluctuations may or may not be correlated. In our case, they are, and they have to be because of the continuity equation. And this gives rise to a number of complications and to a number of nice effects. All right, then we had to introduce a Green's function for solving the free equations of motion. Also, that was independent of cosmology. Right? The actual shape of the Green's function, this will of course reflect the expanding background and the Hamiltonian and so forth. Right? But the fact that you will need a Green's function in order to evolve particle trajectories forward, independent of cosmology again. And once you're done with that, you know everything that you need to know. You need the initial state, you need the Green's function. From then on, the generating functional of KFT is set. And you can apply this to, I don't know, complete different system. For example, you could apply KFT to an ideal gas. This would be completely uninteresting, but of course you could. And then what would you have to do? You would create an initial state that would not have any density fluctuation, that would have momentum fluctuations such that any pair of momenta would be uncorrelated. Right? So any two different momenta, that is, momenta at two different positions, would be uncorrelated, and the momenta would be characterized only by a variance. And for the ideal gas, the variance of the local variance of the momenta would be set by the temperature. And then you could apply KFT to the ideal gas, and it would give you completely boring results. But of course you could. And then you could start adding further complications. All right. Now, specializing the whole thing to cosmology means, first of all, that we have to set the initial state in an appropriate way, and that we have to choose the Green's function appropriately. And this was one of the key points of the lecture, right? Seeing that, first of all, how we can port the Hamiltonian equations of motion to an expanding space-time. And there we used several transformations, among other things, the invariance of particle dynamics under additions of the form df derived with respect to dt to the Lagrange function. And we used that in order to get rid of a number of terms in the equations of motion, to transform the equation of motion to co-moving coordinates. Then we also saw that we can map the expansion of space-time to a time-dependent particle mass. This was an equivalence transformation. It's no approximation involved. But this reflects the fact that if you have particles at a certain fixed separation in co-moving coordinates, their physical separation will increase, and the interaction with them will weaken. And so if you map this to an increasing particle mass, it means that a given interaction force between the particles will have less effect. But the transformation is an equivalence transformation. All right. And that was essentially it. And then we constructed a Green's function from there. And we saw that in constructing the Green's function, we have a choice. Right? We have a choice of introducing a fiducial particle trajectory, which we call force-free. And we saw that in cosmology, there is one particular choice of reference or fiducial trajectory, namely given by the Seldovich approximation. And it's preferred because, first of all, then the free motion already reproduces linear structure growth. And it's preferred also in view of the fact that then the interaction potential between the particles relative to these fiducial trajectories loses the long range. Right? It becomes a short-range interaction, which is, as we saw, approximately of Yukawa form. And this makes perturbation theory, for example, much simpler. And it also means that already the 0 point of, for example, a perturbative ansatz already reflects the linear structure growth. Why can it do that? So why can free motion in the Soldovich approximation already reproduce linear structure growth? It can do so because we are assuming that momentum fluctuations are correlated with density fluctuations. So the attraction exerted by positive density fluctuations leading to converging matter flows is already included in the initial conditions, right, by taking the continuity equation into account. And this is enough to reflect the linear structure growth. All right, then we have a generating functional, and like the partition sum in ordinary equilibrium thermodynamics, the generating functional contains all the information on the particle ensemble that you want to have. And then, by means of suitable operators, you can extract this information from the generating functional. And essentially, we define two of these operators, a density and a velocity, what we call the velocity operator, but it's actually a momentum density operator. And we extract the power spectra from there. And we saw that the form of the density operator, for example, being a derivative in the argument of an exponential, just leads to a macroscopic shift of the generating functional. And this allowed us to factorize the generating functional and move on from there. And finally, we talked also about how we can include particle interactions into the generating functional. I showed you two different ways. One of them is by expanding the interaction operator into a Taylor series and developing perturbation theory on top of that. And the other one was a mean field approach, which I showed you was quite successful, but not rigorously derived yet. And essentially, that was the end of the story. We also talked about velocity correlations last time. But the overview is summarized in a very concise way. What you need for KFT is an initial state plus a Green's function. Then you can derive statistical information on the particle ensemble by applying operators. In the simplest case, with a density operator, this will just create a shift of the generating functional. Then you can read off power spectra. Underlying the whole theory, underlying the whole lecture, is the definition that structure is the presence of correlations. So what you learn in this way is how you can calculate correlation functions in principle of arbitrary order from this approach. It does not give you the possibility to produce pretty pictures. Why is that? Because we only have statistical information, and since we start from a Gaussian random field, we ignore the phases of the density and momentum fluctuations and only take their amplitudes into account in calculating power spectra. And of course, it's the phases that you need in order to get the pretty pictures. If you want that, you need something else. What we gain, or what one of the main advantages of an approach like KFT is, first of all, that you can analyze the structure of the theory in order to search for universality, for universal properties of structures forming, number one, from a Gaussian random field, number two, under the influence either of free streaming or of gravity. And I showed you two aspects of universality that we could derive from that already. One of them is very well known since the 1970s, and it's the fact that starting from a Gaussian random field, spherical collapse is forbidden, right? Which leads to the network-like structures that we observe in cosmology. Second, and this is a new result based on KFT, is that the free power spectrum necessarily acquires a k to the minus 3 asymptotic tail going to high wave numbers, and that is going towards small scale. In the mean field approximation, it seems that, mean field approximation as we have it now, it seems that interaction will not change this asymptotic tail, and this would mean that structures become self-similar on small scale. That's approximately where we are. We have used KFT also to study other things. For example, if you think of what the cosmological dependencies are that actually enter into KFT, then this is a minimal set of requirements, or a minimal set of influences. Essentially, cosmology enters into KFT only through the expansion behavior of the background spacetime. This controls what the Green's function looks like. This controls how the effective particle mass depends on time, and that is it. So this would mean that whenever your cosmological model, or whenever your possibly modified gravitational theory gives you the same integrated time evolution of the background, it will give you the same evolution of the structures of that background. This is another aspect of universality. And this means that within the framework of an analytic theory like this, you can address also questions of the sort, if I modify my theory of gravity in a particular way, or if I modify the expansion behavior of the background in a particular way, how will nonlinear cosmic structure growth be affected? According to what we have found so far, very, very little. What this means is that cosmic structure formation is essentially insensitive to details of the cosmological model and to details of the gravitational theory. What this means in return is, studying nonlinear cosmic structure formation, you can't learn very much about these things. This is the backside of universal behavior. All right, that's what I wanted to say for summarizing this lecture. As I told you last time, I haven't touched on many other aspects of KFT that we have studied in the meantime, mainly because I don't think they are appropriate for a lecture, at least not in the form that we have now. All right. That's what I wanted to say from my side. Now, if you have questions, feel free to ask them.
Really, so what other applications? What has
We have applied KFT to Rydberg gases. Rydberg gases, right? Essentially cold quantum gases in quantum states which are so highly excited that quantum entanglement or quantum correlations don't play a big role. And what we found in this way, for example, was that you can predict the evolution of correlation functions and thereby the evolution of optical properties of these Rydberg gases in a very nice way with KFT. That's the other end of the spectrum, cold quantum gases and cosmology. But as I said, the method is sufficiently general to apply the theory in exactly the same way. You need the Green's function and an initial state. And once you have that, go ahead. Yeah, no problem. If you want to know more about this, ask Elena Kozlikin, who just submitted a paper about this, together with experimental physicists. You mean the J field or the K field? Yeah, they are only there for you to apply functional derivatives. And once you have done so, you throw them away. Yeah, it's yeah, it implements what is also known as the Feynman trick. Right? When you suppose you have to solve an integral like that between some boundaries and with some exponent here, you can write this as we can solve this and apply derivatives. Now, suppose you want to have that. Yeah, you want to have an integral like this. You leave this here, apply these operations, and then set x to 0. What we are doing is essentially exactly the same thing. We introduce a source field to have a functional dependence that we can use in order to extract statistical information by applying differential operators. Yes. So we have applied it so far now from initial redshift 1000 to redshift 0. So I showed you an example of the mean field approximation for the nonlinear power spectrum, and where you have percent level differences between the KFT result and the fully numerical result. And this was down to redshift 0. So we did the comparison at redshift 0, so at the cosmic present, and we went to wave number k equals 10. And if you compare this, for example, to what alternative analytic approaches can do, they typically fail at redshift 0 above a wave number of approximately 0.3. And this is exactly where the velocity field becomes multi-valued. So far, I don't see any limitation in principle for the application of KFT to cosmology. It may be difficult to calculate all the ingredients, but there is no conceptual breakdown. Well, for example, if you consider the evolution of cosmic structures over the observable redshift range, then of course you would have to calculate power spectra from redshifts, let's say 2 to 0 or so, and that's also possible in principle. Calculate or constraining the initial state is difficult because very similar different initial states can lead to very similar behavior at the end because of universal evolution. And we believe that we know the initial state much better than the final state from observations of the cosmic microwave background, for example. So it's rather the other way around that we want to go.
One of the exercises we transformed into to tell you about function. I'm not sure right now which function we used at the beginning, but I know what the Cataneo function what's the result with that? Why we want to do that?
The honest answer is because we were helpless. -1 or not, it doesn't matter very much. So this is our main problem. And bless you. You have an oscillating integrand with a possibly enormous dynamical range. So this integrand goes like that. And the computer goes crazy when you ask him to integrate that. Because essentially every positive half wave of the integrand is immediately cancelled or almost cancelled by a negative half wave. And so the computer ends up summing up essentially numerical noise. Now, of course, you can play tricks here. And first of all, you can subtract this 1 here, which already helps a lot. Then, as you did in the exercise, you can do that and subtract the next order in the Taylor expansion of this exponential here as well, because you know the analytic result here. It's a linear power spectrum. Okay, fine. And then the convergence behavior of this integral has miraculously improved by quite a lot. So that was the first step towards the Faddeev function. And then you wonder, okay, now I have to carry out a 3-dimensional integral. 1 dimension, namely the azimuthal angle, that's trivial. Let's not worry about this. And then the next step would be to integrate over the angle cosine here between k and r. Okay, if you do this blindly, you come up with a Bessel function here, spherical Bessel function. But in fact, what you have is an integral over a Gaussian here. And this leads to the introduction of the Faddeev function. And our hope was that, since the Faddeev function is very well known from plasma physics, that you can use numerical implementations of the Faddeev function in order to simplify the numerical evaluation of this thing here. So this was the aspect of helplessness. Now, on the way, you find a number of very interesting things. So if you don't get paralyzed by your feeling of helplessness, some interesting things happen. First of all, you find, and this was the key point of asking you to do this on the problem sheet, is that suddenly you realize how this exponential damping that you see in the first evaluation of the power spectrum, how this gets cancelled. Right? Writing this in terms of the Faddeev function tells you how the exponential damping goes away. And we had first found this by studying the asymptotic evolution, seeing that this is not asymptotic, this is not exponentially damped, but the power spectrum falls off like k to the -3 rather than exponentially. And then we wanted to understand, why the hell don't you see this here? Introducing the Faddeev function, you see how this goes away. This is one positive aspect. And then you also see how you could write the result of carrying out the mu integration, which leaves you radial integration. How you could decompose that into integrals over sines and cosines. In other words, how you can transform this into a 1-dimensional Fourier transform. And then you might hope to apply numerical methods for 1-dimensional Fourier transform, fast Fourier methods, in order to solve that. I haven't tried this yet, but this is one of the aspects of going into this direction. So the knowledge of the Faddeev function from plasma physics the recognition of where the exponential damping goes away, and the hope to transform this to a one-dimensional Fourier integral. These were the driving elements. And then it's a nice exercise for you to do.
Why is the Candela function more beneficial for us, or why do we think it's better for us than the error functions we obtain on the way doing that?
Because you have numerical implementations of it. There's a very, very reliable numerical implementation of the Fadeba function, which has been developed at MIT, and this we wanted to borrow. That's what we also thought. All right. You wrote me a mail saying you would have questions, so I'm waiting for them.
Would you mind giving an overview over all power spectra and what they actually mean? I mean, there was a P delta, there was a psi, there was a curly P, there was a G somehow. And they were all called power spectrum. You got a little confused which one would mean like what?
Okay. So generally, a power spectrum is the variance in Fourier space of whatever you want to know. So this is the reason why so many things called power spectrum appear. Variance in Fourier space, no more, no less. Now, the variance of what in Fourier space is a different question. And we looked in particular at three of them, namely density fluctuations, velocity fluctuations, and velocity potential fluctuations. So these were the essential three things that we looked at as P delta, P psi, and P capital pi. We had things that looked like this last time. All right. Now, the difference between this and that is that this is linear and this is nonlinear. So if you look at the variance in Fourier space of the linearly evolved density fluctuations, I would write them with this P. And if you looked at the variance in Fourier space of the nonlinearly evolved density fluctuations, I would write them like this, just in order to avoid that I always have to write or things like that. I think so, yes. Or did I mess this up, Christian?
Is basically the kind of nonlinear but not technically.
Well, yeah.
Okay. I would call it nonlinear.
I would have come to that, yeah. So the nonlinearity that I mean here is taken into account with this exponential function here. If you approximate the exponential function just by its first order, then you get from here to there. Then come the interaction, and then you get the fully nonlinear part. All right. And then there were the G's, in fact. So the P's, the notational convention in cosmology. If you look at the convention in statistical physics, people often write capital G for any kinds of cumulants, correlators, power spectra, and so on. So one meaning of the very many G's that appear throughout the lecture is that this is an average over the result of applying many different operators to the generating function. So you pick out an operator of your liking, density, velocity, blah, blah, blah. You apply this to the generating functional, and in that sense, carry out the expectation value of the product of operators. this will be a correlation function or a cumulant. If the correlation function is in real space, you call it a correlation function. If it's in Fourier space, you call it a power spectrum. So this is a more general notation common in statistical physics, also in quantum field theory, for example. Maybe because this could also be read as a correlator. I don't know. And then if you specialize this to cosmology, the more common notation is the power spectrum P. The word power spectrum comes from applying this to the theory of electrical transmission through cables. This is where people first analyzed the statistics of electrodynamical noise in power cable. And then the variance in Fourier space does in fact have to do with the transmitted power, or with the electrical power in that noise, which heats up the cable and so on. So you would really want to know that. And this is where the quite unfortunate term power spectrum comes from. Cosmology doesn't have to do anything with power. But where this whole theory first came from, it has a lot to do with the heating power of cables by noise, ohmian noise. All right. Does this answer your question? Yes.
So in the nuclear approximation, we calculate the benefit for the one particle like our reduction. We have a K0, which means this is zero time. From this case, zero is always free.
It means the following thing. Or we introduce it to indicate the following thing. This was the Poisson equation for that particular type of potential. Now, at small wave numbers, there will be no nonlinear density fluctuation. At large wave number, there will be. There must be a transition somewhere. And we call the wave number where nonlinear density fluctuations set in K0. Right, so, for example, if I illustrate this with a cold dark matter power spectrum, the linearly evolved spectrum would look like this. The non-linearly evolved spectrum would look like that. So there is a scale somewhere in between where the nonlinear density fluctuations set in, and this would be the K0 here. Now, of course, this depends on time, right? Because initially you do not have any nonlinear density fluctuations, and then K0 is infinitely large. And as time proceeds, it will start moving inwards. So this K0 is a function of time. But this was just the notation that we chose for distinguishing between linear and nonlinear scales. I do. Do I have connection? No. But of course, I also have a local copy. Smart, eh? Okay, where do you want me to go? First of all, these y's should be q's here. Sorry for that. That's an internal spatial variable that I need to integrate over. Okay, this just means the following thing. As you said, this is the Fourier phase. Let's not worry about these. Let's worry about those. These are delta functions. And they pick out any 2 points between which I want to take the correlation.
I would kind of understand if Q1 minus Q2 or so, but I don't see why it's the sum of delta.
So what I'm doing here is, in the first line, I write down the relation between the Fourier modes acting with fixed points Q1 and Q2 on variable point y. And I need to integrate, Q it should be, right? I'm integrating over all Q. In other words, here I'm looking at the effect that a density fluctuation at point Q of wave number k has on points 1 and 2. Density fluctuations, point Q. I have fixed set of points Q1 and Q2 here. And now I'm integrating with Q all over all possible positions. And I'm looking at the force difference that this density fluctuation exerts. All right, and now I'm picking out those density fluctuations from which the points Q1 and Q2 are actually drawn. In other words, now I'm specializing all possible density fluctuations such that only the density fluctuation, only that particular density fluctuation acts on point 2, where point 1 is located, and the reverse. In other words, here I'm neglecting all 3-point correlation. Right here, in this line, I'm saying I'm only taking the correlated force on this particle from the density fluctuation where this is from, and on this particle from the density fluctuation where this is from, not from a third point. Assuming that I could neglect in a Gaussian random field the 3-point correlation. This is a crude assumption here, and it's dubious, right? Because usually you would assume that even if you do not, or even though you do not have generic 3-point correlations in a Gaussian random field, you would have the correlations between these 2 points, these 2 points, and these 2 points. These are all 2-point correlations, they must add up. This effect is not taken into account here. And this is why on problem sheet number 11, you find the complete calculation. All right, and then, so once you buy that, right, once you're willing to accept that, you're just specializing the density fluctuations acting on point 1 and on point 2 to particular values, and then the whole calculation goes through. But this is a critical step, yeah. And one that I'm trying very hard to get rid of now. I mean, the mean field approximation gives you very good results. On the other hand, this is something very hard to justify. And it's not so hard to do better. I just didn't come across that early enough. You had more questions, right? These are very specific questions. Okay. Okay, what do you want to see first? 462? There are so many equations. I mean, 462.
Yeah, the EJI.
All right, yes. Okay, that's a subtle point, and one that gives rise to a lot of confusion. Obviously, it worked also for you. Remember, we applied one particle density operators. Let me write this down. So we want to have a complete density operator. This would be that one. But then applying this whole sum to the generating functional, each one with a one particle density operator, is a complicated thing to do. Rather, we do something else. Right? We say, okay, I'm now applying a certain number of density operators to the generating functional, maybe to the free generating function. And then we said, okay, now it doesn't matter which particle I pick, because all these particles are indistinguishable. So then, this density operator here, if it was a complete density operator, would have the n-fold effect of applying a single particle density operator. Because I only extract statistical information, not individual information, and all the particles are indistinguishable. So this is why we then wrote, instead of applying the sequence of complete density operators, we said, okay, this is n to the power of the number of the density operator. Let's call this L, right? If there are L of these. And then we have one particle density operator. Okay? Huh? So suppose I only want to apply a single density operator here. Then I write this as n times rho I of z. Again, saying that one particle density operator will extract representative information for all n particles. And now I'm doing this L times here. Okay. So now I have the problem of enumerating these particles. Now I could say, okay, I just enumerate them as 1 to L. This may be too restrictive. So let me rather say I enumerate them with indices I1 to IL. Because I want to have the freedom to fix the enumeration later. This could be rho 1 to rho L, and there may be no problem with that. This could also be rho 17, rho 353, rho 797, rho 1, and so on, right? So I need to pick individual indices for these particles if I want to be completely general. Now, in very many applications, I can just write rho 1 to rho L. This would be one particular choice of these indices, but not a general one. Now, later, I will have the problem of saying that I need to apply the density operator corresponding to a certain wave vector. And then I need to enumerate that wave vector and the particle representing this wave. Then this is the general way of writing this down. Because the particle representing this wave is arbitrary. And if I fix the same index to the particle and the wave, this may lead to confusion. And this is why we keep these indices separate if we need to. There are many situations in which I can represent wave number one by particle number one, but not in general. Now, if you look at where we applied this, if I'm just calculating a free power spectrum, it just doesn't matter. And then I can easily identify IL with L. Sorry. In fact, an IJ here, right? And J runs from 1 to L. I can easily identify IJ with J. Strictly speaking, it should be JI. Right? It's the particle index representing wave number I. So the I must be a subindex of J, not the other way around. So in very many applications, I can just set Ji to I and everything is fine. But then you realize when I apply these response field operators that I need in order to take interactions into account, I need to have the Kronecker delta. And once you write these down, and you would write them just with the indices I here, you would at the same time where you identify two particles, also identify two wave numbers, and that is getting wrong. And this is where you definitely need to distinguish them. So most of the time you don't make any error and you don't cause any confusion if you just set Ji to I. But when you're getting to taking interactions into account, go back to the general enumeration in order to not identify with the Kronecker deltas things that you must not identify. All right? I'm aware that this is confusing. It confused us as well. And it confuses everybody who comes new to our group and so on. But this is the reason. Okay?
Yeah.
Let's have a look. Yes, it is. This is exactly the case that I was mentioning. Right here you have response fields. And then you will, by each introduction of a response field, you will identify two particles. This gives rise to the Kronecker delta. I'm speaking of those, right?
Yeah.
And here you say it's JSJK, not a KS, because you don't want to identify these wave numbers. God forbid.
Actually, it's about 690. We're summing over S, right? How does the sum collapse? I mean, how does the delta? The sum should collapse because of the delta.
Yes. Now let me draw as an answer one of these diagrams that we made. And I heard from the Celine that you like these diagrams very much in the tutorial. Yeah, beautiful, aren't they? They will not appear in the exam. I'm drawing an example where I do not actually sum over S because there is only one of them. But I start with them. Can project a lot of fantasies into that. Okay. So what was that? That is a first order interaction diagram for a 2-point function. Right? We have wave vectors k1 and k2 here. We have an interaction represented by a response field here. And now we could, for example, indicate one of these Kronecker deltas by this identification here. All right, so this would be k1 prime. This would be minus k1 prime. This is minus k1 here. All right. Now I'm assigning particles now to these wave vectors. So this means now I make a choice for the collection of JS or JL. Okay, I just start counting here by 1. I could start by 17 as well, or by 3,200,573. 1 is easier. Again, I could take a completely random number here, or just 2. Then this one is also free, but this one is not anymore. And this is the Kronecker delta here. Right? So this is 1 again. So now you have the set of JS, which is 1, 2, 3, 1. And the Kronecker delta would be this one. And now you're not summing over anything because the sum would be over response fields and there is just 1. Eats up the sum. I like this term. Yeah. See, now you're summing over all the wave vectors, but you keep the wave vector that you have assigned to a response field fixed. In this diagram here, you keep the k1 prime minus k1 prime fixed. Now you want to sum over this? No. The Kronecker is 0. Right? You start here, then you go forward. Delta 3, 1 is 0. Delta 2, 1 is also 0. The only one where it couples is this one. And there's only that one remaining term. Hello? There's only that one remaining term in this sum over. Right? So this is a sum over all these wave vectors. And this collection of indices decides which of these you couple. All right. Now, more challenging example. Suppose you have a situation like this. In other words, that's a contribution to a second order interaction to a 2-point function. So we have k1 minus k1, k1 prime, minus k1 prime, k2 prime, minus k2 prime. All right. Now I need to introduce 2 response fields, right? Because the interaction terms need to couple to something. That's the meaning of the term interaction. All right. This is 1. And this is a possible other one. All right, now, again, let's assign particles. Starting with 1. Boringly. Okay, 1. This is not coupled to 1, so I give it a 2. This is not coupled to 1 or 2, so I give it a 3. Maybe. Let's see if this is garish enough. 1, 2, 3. All right, now this is coupled to one of the previous. And this is coupled to 1. So this is also 1. This is free, so it gets 4. If somebody watches us that doesn't know, who doesn't know the rules, right? Sounds completely odd. Okay, now this is identified with that one. So this is 3. Okay, now the set of indices is 1, 2, 3, 1, 4, 3. Okay, and now in the summation, over all of these indices, these two are coupled, and these two are coupled. So you see that if you pick out one of these response fields, that one or that one, so that one or that one, the Kronecker delta picks out exactly one partner, and so the sum collapses to a single term. See, here I fixed one of these wave vectors corresponding to picking out either that one or that one. Here I am summing over all, which gives me these two, this pair as single contribution, or in that case here, this pair as the single contribution. And this is the only remaining term here. Now, of course, you could say, wait, if I pick out this one and I sum over all the wave vectors, then I would also have to sum over this one multiplied with itself. Because delta 3, 3 obviously is also would also contribute. But here the times are the same. And propagator says, I give you 0 back. Good. Very confusing, I admit. In the exam, we will look at fifth order perturbation terms. I think this would amount to approximately 600 different terms. Says the computer. I wouldn't do this. All right. Anything else? Ice cream, anybody? Coffee? Yes. I don't know. And if you find one, you are most welcome to let me know. So meanwhile, apart from myself, I think 5 or 6 different people have tried to find a rule for calculating the number of equivalent permutations in these diagrams. Among them are Shafak, Christoph, Robert, and several other people. We have not succeeded in finding a general rule going beyond, I think, third order. I really don't know. Oran, of course. Oran, who is not here. He also made a big step forward, but also to second order. I really don't know. And I have to say, about all kinds of combinatorial questions, my brain is really dysfunctional.
Yeah,
so with combinatorics, I'm really bad. And then I asked somebody who said, I'm really good at combinatorics, please. But then he left his master's project and so on. Yeah.
So it seems science non-linear power but
That's what we are, well, that's part of what we are focusing on, yes.
so non-linear power spectrum science because we define the linear function, we are using already the linear power spectrum.
Yeah. No, well, you could formally derive it as well as the limit of small times of the complete power spectrum. But of course, you know that from the start. Would just be our time coordinate plus 1 squared times the linear power spectrum, the initial linear power spectrum. It gets interesting, however, and this is also the reason why I put this on a problem sheet. If you start calculating the connected contributions to the linear bispectrum, a spectrum of order 3, because there you get some result in KFT and you get another result in hydrodynamic perturbation theory. You remember that problem sheet? Can you have a look at that? There was one problem sheet where I asked you to calculate the lowest order contribution to the connected bispectrum, saying that this would be a product of linear power spectra times some kernel function. There was a kernel function f of k2, k3 appearing, and it looked like 1 plus k2 times k3 divided by k2 squared times 1 plus k2 times k3 divided by k3 squared. That's the KFT result. And it looks very beautiful. And it's different from what hydrodynamic perturbation theory gives you, because there factors of 4/7 and 8/7 or something appear. And we haven't clarified why that is. Meanwhile, I would trust the KFT result more, because in the hydrodynamical approach, you do not get any curl component of the velocity field, while we are getting this. And I think these factors must come from there. But even at this level, since you were asking for a linear spectrum, right? Even at this level, you find KFT specific difference to other theories. And of course, KFT is superior. All right. Anything else? Yes. Yes, of course. Of course. There are. I'm sure there are many. Yeah. Whatever is most convenient. If you have them noted on paper, for example, you could send me a scan of the paper, or whatever is convenient for you. Yes, I'm very much interested in that, because it seems impossible, at least for me, to write lecture notes without typos. Glad to hear that. I have to say, however, that the last sections, I think, were typed by Laura Polter, not by me. So then I will pass on the compliment. All right. Speaking of the exam, there will be 4 problems. The first one will be general comprehension question. Questions like, what is KFT good for? And then you find cleaning your shoes, cooking coffee, kinds of things. And in all these problems, there will be a single correct answer. Wrong answers won't count negatively. This question always comes up. I don't know who does that, but so who would count wrong answers negatively? But okay, seems to be a problem. Good. The next 3 will be for you to calculate things. Now, remember that today I emphasized that you need 2 things in order to start KFT, and then you mostly do 1 thing once you have KFT. You need a Green's function, need an initial state, you need to calculate power spectrum. Now guess what these 3 problems will be about. No more info. Come and have a look. Did you all tell Celine that you want to participate in the exam? If you want to participate in the exam, it's nothing binding for us. We just need to know how big the room has to be. And it seems that a room of this size will be large enough. So for the moment, think of coming here if you want to participate. All right. Anything else? Yes. What do you have in mind? That's a very interesting aspect that we haven't looked in depth at now so far. What people measure are correlations in redshift space and not correlations in configuration space. And KFT in principle allows you to extract redshift space power spectra as well. We haven't done so yet, but this is a very interesting application. Also, as you saw, what we are usually assuming is that we want to calculate synchronous power spectra. We are correlating density fluctuations at the same time. Likewise, you could calculate power spectra at 2 different times. This could also be most interesting for cosmology, for example, if you cross-correlate an object along this line of sight with gravitationally lensing density fluctuations along the other line of sight. Then you would have to take, or we could take into account asynchronous correlation function, correlating that particular source at its time with density fluctuations at all times in between. But we haven't looked at these things so far. They can be easily calculated. If there are no further questions, then we conclude for today. Thank you very much for your attendance, for your attention, for your participation. As I told you last time already, this lecture was an experiment, and I'm very happy with how it came out. So I hope you had fun. I did. Some weeks I really felt pressurized. How am I going to talk about this? Well, I hope it succeeded more or less. Okay. I guess we we'll come across each other in the weeks to follow, even if you don't take part in the exam. So thank you, and bye-bye for today.